Section 2.2, the limit of a function, from OpenStax Calculus Volume 1. At the bottom of every page, there's a link to actually go to the text. The entire textbook is free, so please check that out. These notes are meant to go together with that. So the concept of a limiting process is the most important thing in all of calculus. Okay, so this concept we're going to touch on here with functions builds, okay, when you get to integration, when you get to Riemann sums, particularly is where that comes in, and lots of other things, the derivative. A limiting process is a big deal. So we want to make sure that we understand what's going on here real quick. So we have a definition here, the limit of a function. Let f of x be a function defined at all values in an open interval containing a, some value a, with a possible exception of a itself. And let L be a real number. If all values of the function f of x approach the real number L as the values of x, not equal to a possibly, approach the number a, then we say that the limit of f of x as x approaches a is L. More succinctly, as x gets closer to a, f of x gets closer and stays close to L. Symbolically, we write this as the limit as x approaches a of f of x equals L. So the idea here is what happens as you get close to a value. So on each of these graphs, what happens around the number 2 as x approaches 2? Well, here is x equals 2. Around that value, what's happening? Well, the y values of a, this first one, the y values are approaching this value, which is 4. Okay, so we're approaching 4, it appears like there. Okay, what's happening on part B? As our x values approach 2, from this direction we have one thing, and from this direction we have another. Okay, that doesn't feel good. Okay, and then this last one, as we approach the x's coming from this way, and we approach that value of 2 going from this way, we get something crazy happening. Okay, so the basic idea here is what happens to the y values as the x values get close to a. So before even thinking about finding a limit graphically, say out loud what the notation means. Okay, read it as x approaches 2, the y values approach what? That's kind of the question we want to ask. All right, so let's begin looking at some of these with tables. All right, so we've got graphs. We'll look at some graphs and tables. So consider making a table to evaluate the limit as x approaches 0 of sine x over x. And check the result with a graph. Okay, so I actually have graphs over on the side of all of these. But if I were going to plot these with a table, if I were going to use a table for my limit, since I want to know where x is close to 0, I might try something like negative 0.1, negative 0.01, or positive 0.01, positive 0.1. So from the negative side here, the negative 0.1 is 0.99833. Negative 0.01 is 0.99998. All right, let's start at positive 0.1, 0.99833, 0.99998. Okay, so what happens as we approach 0? 0 is in the middle here. Actually, let's put that over here. 0 is over here, in between those values. So what is happening to the y values? Well, the y values here are approaching 1. Okay, that's the idea of using a table. We want to plug in values that are very close to what we're evaluating our limit at. Now, if I look at my graph, okay, so it appears that this limit equals 1. If I look at my graph, from the left and from the right, the y values are approaching 1. So that does line up with our tables. Okay. Now, this graph right here actually does something really interesting looking. It does something like this. It gets closer and closer to 0 as you go out to the ends, to infinity. Okay, which we'll look at that a little bit later too. All right. Evaluate number 3. So part A. So here are the two graphs here. As we approach 4 on this one, I'm going to go ahead and just appeal the graph. As we approach 4, going from the left and the right, it appears, actually, now you can't see the scale over there, but that is 1/4. It is approaching 1/4. Okay. Now, for part B, as we approach 1 from both directions, we are approaching a y value of -1. So there's our value there. All right, let's hit some more graphs. Find the limit of each of these using the graph. All right, so as x approaches -8, so as x approaches -8, so that would be approaching this. So our y values are getting very close if we follow along that graph. They are approaching a value of -6. So there's our limit for that one. As we approach -2, we are coming up to this. Okay, from one side we have that. As we come from the other, those two don't quite go to the same place. Okay, so this does not exist. DNE. We'll have a formal statement of that in a second. As x approaches 6, +6, we have the same oddity there, so this does not exist. As x approaches 10, okay, there we have something. Our y value at that point is 0. So both sides are approaching a limit of 0. Okay, number 5. The limit as x approaches 0 of sine of 1/x. Well, if we look at our graph, what happens with this is our function does this. Okay, as we approach both sides, it oscillates wildly between -1 and 1. Okay, it goes back and forth, back and forth. So this one also does not exist. It doesn't actually approach a value at all. It just goes, like I say, back and forth, very fast. So we say that this limit does not exist, as we've had to say a couple of other times. We have to be kind of careful to look out for things like that. It has to approach and stay close to a value. So it appears to approach 1, but then it doesn't stay very close to 1. It bounces back and forth away from it. Okay, so we have to be aware of that. All right, number 6. Again, I want to look at our graph. And it's as x approaches 2. So we are looking at this value right. There's our x value. So as we approach that, well, those two do not meet. They do not meet in the middle. So our answer is going to be it does not exist. And so this example prompts us to maybe consider this question. Is simply saying that the limit doesn't exist, is that enough? Is there anything more we can say about what's happening at that point? We've had this happen a couple of times where, from one side we see one thing, from the other side we see another. Well, what happens if we just consider the one side? Then we have something called a one-sided limit. So let f of x, let's put all that right there, let f of x be a function defined at all values in an open interval c, comma a, and let L be a real number. If the values of a function f of x approach the real number L as the values of x, where x is less than a, approach the number a, then we say L is the limit of f of x as x approaches a from the left. From the left. Now we will write that in this way right here. It's the limit from the left. Now you may not see it, but it is this little minus sign right here that is saying we are coming from underneath the value of a. And we have a similar idea for the limit from the right, and that is there's a little plus sign right there indicating that we are coming from above the value a. So we can have a limit from the left and a limit from the right. All right, so let's look at some examples. Evaluate each limit given that f of x equals x plus 1 if x is less than 2, and x squared minus 4 if x is greater than or equal to 2. Okay, I'm going to sketch what that graph looks like. So as long as our x values are less than 2, then the function is like x plus 1. Okay, well, x plus 1 would have a value here with a slope of 1, and we would continue that way, and we would have an open circle because we're not equal to 2. So we have a graph that looks like that. And it appears to be a parabola as long as we are greater than or equal to 2. Okay, so at the value of 2, that function is 0. So we'll have a closed dot here, and it is continuing this way because we're not going to write this in here, but it actually is a parabola. It's going down to that point, but we're only considering past 2, or greater than or equal to 2. So I'm going to delete that. Okay. So as we come from below 2, the part that we are considering for part A is coming in this direction. So if we're coming from that direction, the y values appear to approach 3. All right, simple enough. Well, what if we're coming from above 2? What if we're coming from above 2? That would be the limit from the right. That appears to be approaching 0, so our limit is 0. Now, if those two limits were the same, we would say the limit overall exists. So notice that big difference there. All right, now let's look at another function we previously looked at, the absolute value of x squared minus 4 over x minus 2. We had the same graph earlier, except now if we are considering from the left and the right, okay, there is our x value of 2. As we approach from the left, the y values of that function approach negative 4. However, if we come from the right, those y values approach positive 4. And again, if those were the same, then we would say our limit exists overall. And that is where this theorem comes in. Let f of x be a function defined at all values in an open interval containing a, with the possible exception of a itself. Remember, we're only interested in getting close to it. We don't necessarily care what happens at the point at this point yet. And let L be a real number. Then the limit as x goes to a from the left of f of x equals L. Oh, there's no left. The limit as x approaches a of f of x equals L if and only if the limit from the left of f of x equals L and the limit from the right of f of x equals L. If the two limits are the same, then again, I'll say that again, we can say that the limit overall exists. Now the next thing we have to say here, we have a lot of definitions, these are important, is if a function is defined at all values in an open interval, if the values of f of x increase without bound as we approach that value a. Okay, so as we approach a, if the values increase without bound, then we would say, depending on which one it is, the limit as x approaches a from the left is positive infinity, or from the right is positive infinity. So depending on which direction we're coming at that. And then the same idea, if it decreases without bound, then we say the limit is negative infinity. Okay, so just like before, if the limits are equal from the left and the right, then we say that the limit overall is equal to that same limit. Now here we are going to say if the limit from the left and the right are positive infinity, then the limit as x approaches a is positive infinity. Okay, and similarly for negative infinity. And if any of these happen, we go ahead and call that a vertical asymptote. All right. So rather than saying does not exist, we have a special case here for it going directly to infinity. All right, so let's evaluate each of these. So the limit from the left of 1 over x. All right, well, 1 over x, okay, the function y equals 1 over x, has a couple of asymptotes, a vertical asymptote, a horizontal asymptote, and the function is something like this. Now, I know what that is intuitively as a reciprocal function, so I can go ahead and sketch that and use my graph. However, I can always plug in values, just plug in numbers that are very close to 0, and in this case that are negative, they are less than 0. So these are all going to negative infinity. All right, coming from the right, appealing to that same graph, they are going to positive infinity. They're getting larger and larger at that point. So the limit overall does not exist. limit overall does not exist because those two limits from the left and the right are not equal. All right. Now, the limit as x approaches 0 is what we're all considering here, of 1 over x squared. Again, I know what this looks like, and it has a vertical asymptote at 0, a vertical asymptote at 0, and also a horizontal asymptote at y equals 0. Okay, so from the left, this limit is positive infinity. From the right, it's also positive infinity, and so therefore the limit overall is positive infinity. That's making note of what we just talked about a second ago with infinite limits. Okay, identify asymptotes of these limits, of these functions by taking limits. Well, as our values come from beneath 2, okay, all of these values, x minus 2, these are going to be negative. These are going to be negative values cubed. So we're going to have a very small number in our denominator, which dividing by that is going to make a very large negative number. So this limit is going to negative infinity. Well, consider coming from above 2. These will be very positive numbers. They all are positive numbers. Cubed dividing by that is going to make it a very large number as our output of our function, which means that we have a vertical asymptote of x equals 2, because that is where all this is happening. All right, last question for this. We're going to appeal to this graph, and we're going to do this several times. So start out with approaching negative 4 from the left. Negative 4 from the left is 0. Negative 4 from the right is also 0. So the overall limit is 0. And the value at negative 4. We have a value at negative 4, and that is also 0. All right. Well, let's find the limit as x approaches negative 2 from the left of f of x. Limit as x approaches negative 2 from the right of f of x. Limit as x approaches negative 2 overall of f of x. And f of negative 2. Okay, we want to find all those. We're going to repeat this process for these different values. All right, so at negative 2, coming from the left, it appears to be a value of 3. Coming from the right, it appears to be also a value of 3. So the overall limit is 3. And the value at that point is actually undefined. At that point, it is undefined. Okay, that is worth noting. All right, next, the limit as x approaches 1 from the left. Okay, the limit as x approaches 1 from the right of f of x. Limit as x approaches 1 overall f of x. And f of 1. All right, so coming from the left of 1, positive 1, we are approaching 6. Coming from the right, it appears that we are approaching 3, which means that the limit as x approaches 1 overall does not exist. All right, now the value at that point is 6. Okay. Last one of these, we're approaching 3 from the left of f of x. Limit as x approaches 3 from the right of f of x. Limit as x approaches 3 of f of x. And f of 3. All right, well, as we come from the left at 3, it appears we are approaching negative infinity. From the right is also negative infinity, so therefore our limit overall is negative infinity. The limit does exist because they agree. They agree. Now f of negative 3, or f of positive 3, is undefined. Right, because there's not actually a function value at that point. Okay, well that brings us to the end of our beginning, the very beginning of limiting processes. All right, section 2.2, limit of a function.